Okay, good afternoon. Welcome to session 9, Quantum Cryptography 2. So first talk of the session is improved quantum analysis of stake and low NC. And it's going to work by Jan, Bakshi, Kim, Seo, and Chakrabarti. Chakrabarti will present.
Good afternoon, everyone. Thank you for the introduction, Gautam. We talked about quantum cryptanalysis. This is a new area that we are now trying to explore. So when I suggested that we should work on these problems, the students said this is very trivial, nothing much to be done there. Then I said, okay, you first need to cross the trivial problems to uncover non-trivial settings. And this is going to be very relevant. So this is what I will try to show, that how it is gaining relevance and where are the non-trivial aspects of it. So first, a brief background of this problem, what we are contributing, and what is the main summary of this work is we improve the quantum circuit implementations of SPEC. If you are familiar with the various kinds of ciphers, SPEC is an important cipher that has been proposed a few years back by NIST. And in the SPEC quantum circuit design, we did the parallelization of quantum adders by proposing a half-round function and half-key schedule. And then there is a cipher called OMC, for which we found that there has been a work in Indocrypt 2020, where there were some issues in the estimation of resources. We patched those issues before the corrected implementations. We also conversed with the authors about it. And independent to that, we also improved the implementation just by itself for the OMC. And finally, we do the post-quantum security evaluation of SPEC and OMC by invoking the circuits within the setting of global search. So many of you are probably familiar with what's happening in the world of quantum computing, that the capabilities of quantum computers, these are growing over time, so we can have more number of quantum gates and more qubits, which are threatening the ciphers. And the threat is actually very, very serious for public key crypto systems, for which there are already replacements that people started standardizing in post-quantum cryptography. And here we also draw our attention to the cases of private key cryptographic blocks, for which there can be revised and lower security bounds compared to what is claimed in just plain classical cryptanalysis. And what additional is that it can unlock some new kinds of optimization that people may also find very useful in plain classical implementation setting. So here the implementations I will talk about is to be done on a quantum computer. But the kind of optimizations we unlock there to reduce the depth or reduce the number of qubits, the same optimizations in many cases can be applied on a plain FPGA or RTL or ASIC implementations of these ciphers. So the optimizations are applicable on both sides, but we will talk about primarily the quantum structures. So in summary, the implementations are here. We have the different variants of spec, and what we could achieve is significantly lowered depth of the computation. So in quantum, we talk about the number of resources needed, that's the number of qubits, and the logical depth or the depth of a particular gate. So as you can see, in comparison with the previous implementations, we have significantly lower depth. In some cases, that is achieved by increasing the number of qubits, but in most cases, the number of this qubit increase is restricted. That is for spec. And then for the low MC, we have several variants. We started from this low MC, the patched version of the Indocrypt 2020 paper. We reevaluated the number of qubits actually needed there and the depth in that case. Then we have proposed two different variants of low MC implementation. One is the regular, one is the shallow. The shallow version uses less logical depth in the implementation. So there you can see that you can go for significantly lower T depth. So T depth is a metric that we often use to characterize the efficiency of a quantum circuit, because T gate is one gate that takes a lot of resources to be implemented in some technologies. So when we go for higher qubits compared to the Indocrypt paper, then we could achieve a lower T depth by having the shallower version. So this is another direction that we have taken into spec and low MC. So this is the highlight of this, what I just mentioned about this bug fix version and the regular version and the shallow version. So this is basically the summary of the work. That's the main takeaway. And now how we achieved it. What's the backdrop and motivation for this? So there is a celebrated search algorithm for Grovers, where you can start with a k qubit key to be prepared in a superposition state, and then you invoke an oracle, which will run various different keys and just keep on comparing whether it's matching with the cipher text or not. So in one sense, it's basically a brute force search, but we are doing that in a quantum setting. So in Grovers, you get improvement of square root times. That's why if you are trying to call this oracle many times and then the diffusion operator is utilized, this amplitude is something that you want to get off so that the correct answer comes into the in the measurement setting. So this steps 2 and 3 are repeated 2 to the power k times. In classical, it's 2 to the power k order. In quantum, it's square root of 2 to the power k. So this is the very basic setting by which various private key cryptographic operators are being attacked. Now, when we talk about the security requirement, the NIST, they have some very specific bounds on what they call as a level 1, level 3, or level 5 security. So if a cipher is at least as hard to break AES 128, then we call it as 2 to the power 170. That should be the setting of a quantum key search. And this is prescribed by a particular paper recommended by NIST. They say if you can achieve quantum circuit efficiency of 2 to the power 170, then it's level 1. If it's 2 to the power 233 or 2 to the power 298, then it's level 3 or level 5 respectively. So the question here is, if you are designing a new cipher and you are doing the quantum cryptanalysis experiments with this, how do you establish whether it belongs to level 1, 3, or 5? In order to do that, you have to design the circuit itself in a very efficient way. So that is what we are setting out to do. And how do we calculate the cost? The complexity of a quantum attack is calculated as the product of the number of gates and total full depth. So this is something which people keep on debating, that whether this is the best representation or not. But it is now, right now, one acceptable method. And NIST does not include the number of qubits because they think the qubit is less serious problem compared to the logical depth or the T depth of a given circuit. So this helps actually assert our implementation because we work towards reducing the depth, and we show that we can reevaluate the security levels for low MC and spec. So coming to the background of basic quantum circuits, we use some quantum gates to implement ciphers. And these are some standard gates which has their classical counterpart as well. But in general, there could be quantum gates which does not necessarily have a classical part. So here, these are very basic gates like swap, C0, CC0, and NOT gates. You can take some combinations of this gate, for example, gates from the Clifford group and T gates. If you take them together, then it is shown that these gates form an universal gate set in the quantum domain. Much like in the classical domain, we have NAND gate that's universal. In quantum domain, we have universal gate set, which means we can start from a given Boolean function or combinational logic. Then we can implement it just by using those gates. How do we do this implementation? Fortunately, there are lots of open source and community-driven efforts to help in quantum circuit design. We picked up one of them in this particular work that is called Project Q. So Project Q gives a simulator as well as a resource counter when you design a quantum circuit. So you can describe your quantum circuit in this simple description, like there is a C0 gate, there is a Toffoli gate, and once you run this whole implementation, so the simulator, then it evaluates whether your result is matching as expected or not, a simple functional verification, and it will give you the number of qubits, quantum gates, and circuit depth, whatever you could achieve. So this is one of the open source project using which you can do the quantum circuit evaluation. There are few others like Qiskit, and there is Circuit from Google. IBM is promoting Qiskit. So all of them have their pros and cons. The results that you are getting from these circuits, they can also be ported into actual cloud actually available quantum computers, which means for a very small scale circuit, you can run it on a real quantum computer and you can get your results. So these papers, whatever we created as the circuits of this paper, they are run on error-free quantum simulation, and we make the relevant codes available in public, so you can start your experiments also this. I will point out to some more open works that can be done beyond this. Okay, so I will talk about the quantum circuit implementation of SPEC and LOMC. For the SPEC family, so there are different variants, and for each variance, there are multiple parameters in terms of the word size, the number of rounds, and the key size. So in short, this is the basic structure of this SPEC round, where we start from these two different variants, and then we reach this x2i plus 3, x2i plus 2. This is the notation for the round function and the key schedule. And one of the main bottlenecks in the quantum circuit implementation is the addition operation that you see, which are available in multiple places in both of this operation. So we wanted to see how we can optimize this part. And the first thing that we did is take an on-the-fly approach for implementing the key schedule. So initially, K0 is used in the first round, and then K0 is updated to Ki during the encryption. So by this, we eliminated the necessity of storing multiple round keys throughout the implementation. Then the second part, when we tried to optimize the quantum addition, we tried to find a technique by which multiple adders can be run in parallel. In the naive implementations, the adders are sequentially arranged. So what we did is we broke the structure and created a half round function and half key schedule update. So part of the round function is followed by part of the key schedule update. Again, the rest of the round function with the final key schedule update. So until the key schedule is completely updated, the round key, that value is not modified because you are still requiring it in the rest of the round function. So the structure of the circuit looks like this. In quantum representation, we have the input. So these are basically qubits, and the qubits, they move forward when being operated on by multiple gates. So in this case, as you see, this is the first part of the round function. This is the second part of the round function. And we do update the keys K0, that's the key, only after both round functions are done. And when we are doing the part of the round key update, this adder would be located in parallel with the first half of the round function. So this is a simple maneuvering of the parallelization. And we do think that this could be also an effective optimization if someone wants to design a very high speed spec in classical setting. But we did apply these optimizations here in the quantum setting. So that was one of the optimizations which helped us to reduce the depth significantly. And another thing that was also left partly open as possible future exploration is what kind of adders we are going to use. And this is another place of, I would say, in the quantum computing research that is really fascinating, that you can go back to your basic mathematical structures and think of how to implement simple blocks like adders, multipliers, square root. And sometimes all these different variants are not properly explored and implemented. So there are, of course, basic implementations of carry look ahead adder or ripple carry adder, but there are a wide number of variants in the classical setting which are not yet ported. So in this case, we simply took one ripple carry adder, and the reason for picking this up is that it requires only one carry qubit for modular addition, and when we are doing this in parallel, we need two carry qubits. So we didn't want to burden the qubits too much. So if you are going instead of this, if you go for, let's say, a logarithmic tree adder, then you can reduce the depth even further, but that would put some taxation on the qubit count. So this is a possibility that we didn't fully explore in this work. So there are many quantum adder designs, like I mentioned, and one can pick up based on the optimization goal, which kind of adder can be chosen and whether they can be used to reduce the depth even further. So depending on the final evaluation platform, if someone wants to optimize on the qubit or optimize on the depth, you can pick up many different variants. So to look into the results for the spec implementation, we did this parallel quantum adder implementation with the CKDM adder as the ripple carry one. This provides a direct implementation improvement of 56% in terms of the depth. So that is the average improvement. And as you can see, the number of qubits are not significantly more compared to the prior implementation. So this is a straightforward optimization that we could get the depth. And the technique for achieving this was going with the half round function and half key scheduling. So going to the other cipher that we were implementing in this work was the low MC. So for low MC, there are again multiple variants depending on the security layers and setting. They have several blocks like key addition, constant addition, linear layer, S-box layer. So we did some optimizations in each of the layers that I will describe now. So starting from the S-box, it is possible to go for a regular or a shallow implementation. So what is the main difference? If you go for a regular implementations of the S-box, then we start from this three initial qubits, which are the three inputs of the S-box. You get the output in place, and there is no additional qubit that I'm using. So additional qubit, also referred in quantum setting as ancilla qubit, can be sometimes costlier. So in many situations, they want to avoid it. So what we do here is, in the other scenario, we add additional qubit because we want to optimize on the depth, which we call as a shallow or out of place S-box implementation. So you can pick up either of them and you get two different variations in the optimization goal. And here I also must mention that S-box optimizations is a very, very well-studied problem in the classical implementations of many different symmetric key ciphers. So these implementations can also be improved by applying the techniques that we have here. Some of the logic synthesis algorithms and flows that people have developed for quantum circuit implementation has been ported for more efficient S-box implementation in the classical setting. So basically the optimizations can travel both ways. So when we go for this two different variants of S-box, then you can see that for the regular version, we have slightly higher T depth and lower qubit count, whereas for the shallow version, we have just a Toffoli depth of 1, and the number of qubits is more in that case, that's increased. So then there is a linear layer of the low MC, which is basically running a matrix operation on GF2 for n cross n, given an n-bit block. So the first implementation that we found for this was in the Eurocrypt paper in JNRP 2020. They went for a programmable logic unit or PLU-based matrix factorization, they did the in-place implementation, which reduces the number of qubits. So that's the first version of our work in the regular version, but it has a very high circuit depth due to the limited space. And what we do in this case for the linear layer implementation, we allocate new n qubit for the result vector. So we free up the space by which we could squeeze the depth significantly. So that allows for more parallelization and reducing the circuit depth. So this is the comparison for this linear layer implementation. When we look into the previous works, then compared to them, we directly go for a double number of qubits, but the depth is reduced by almost 10 times. So which is a very, very advantageous trade-off in terms of our implementation. And if we go for the independent operations between the C0 and other blocks in the low MC, then even in that case, what we see is the depth is significantly reduced. So there is another block of operation for the low MC in the key schedule, where the matrix multiplication can be essentially performed the same way as the linear layer. And there we also applied another technique picked up from the quantum domain, which is the reverse operation, also referred sometimes as uncomputing. So you perform a computation, and the computation is basically stored in a qubit, and you want to reuse that qubit. In order to do that, what you do is you uncompute whatever operation happened here, you free up that space. So that technique allows us to significantly reduce the number of qubits. So in the previous example optimizations that I was mentioning, we are going for increasing the qubits, reducing the depth. And there now we are doing the uncomputation operation, which helps us to again squeeze the number of qubits. So you basically want to take the benefit from the both world. So this is the basic structure. If you go for the low MC implementation, where we have the key schedule, and this is the whole key schedule operation generating the round key here. And after that, we do a reverse operation, which is the uncomputation of key schedule that is again applied on the round key. And after this point, the round key is going back to its own original states. It's simply like applying the XOR operation twice. That's what is happening here. So after this, we can keep on applying the key schedule and the inverse key schedule for following rounds multiple times. So when we do this, what happens is, since we are introducing the additional inverse operation, the depth increases. So in order to compensate for that, we are performing the round key generation in two key spaces. So we generate it twice. So that's for round key 0 and round key 1. So there are many different trade-offs possible here. While the inverse operation is only applied once, if someone wants to go for more parallelism and reduce depth, then they can generate round keys like, instead of 2 key spaces, can be 3, 4, 5, this kind of key spaces. That's also possible. So this is basically the key schedule operation and inverse operation. They can also be run in parallel. So this is an optimization that we also figured out for this. And after combining all these things, when we go for the low MC implementation, what we could achieve is the number of qubit actually now remains the same for the key schedule operation in the prior implementation and in our implementation. So we didn't use even a single extra qubit, but we significantly reduce the depth. So it's almost 1 order of magnitude reduction. So when we go for the performance comparison overall, then we have the matrix multiplication in linear layer and key schedule compared to JNRV, which uses the PLU factorization that incurs high depth. We went for a different approach by which our depth is reduced, but we use more qubits in this particular space. So when we compare the overall results for low MC, then for these 3 variants, we see that we can go for higher qubits. So this is for the whole circuit and not for linear layer or one particular one. And the overall depth is much reduced. If we go for the shallow version, then the T depth is also quite less compared to the basic operation. So there are different, say, arguments in favor of whether one should consider the full logical depth or only T depth. So both are sometimes acceptable as a metric. So in this case, when we are following the complexity of the attack, then we are multiplying the number of gates with the whole logical depth. And that's why we are taking this full depth consideration. So if we look into the previous implementation for the JNRB, then the first thing that we had to do is to fix a known bug for the structure. And that we patched. And the reason for this bug is also, it became apparent that there is a using command in Q sharp in project Q that automatically disposes of the ancilla qubits, which should have been considered in the full implementation. So we corrected the number of qubits. So this is some example which we detailed also in the paper. The correction says, okay, instead of simply 3 ancilla qubits, it should be 30 ancilla qubits for 10 S boxes, because they're running this in parallel. And this is also another bug fix in their CC0 implementation with the T-depth. They didn't consider all the necessary ancilla when they're using many TOEFL loops. So the final evaluation analysis says that when we go for the NIST recommended levels, these are the 3 that I originally mentioned. And on top of that, there are some modified analysis implementation by Young et al., who says that instead of 2 to the power 170, we should consider slightly lower level for level 1 and similarly for level 3 and level 5. When we do compare that, the level of security for the NIST and the other recommendations, 2 to the power 170, 169, and 157, as for our implementation, a lot of spec variance does not meet the security levels at all. And only when we go for a higher level 5 and so on, this variance, they satisfy this level. So this is basically a reevaluation of the complete security level for the spec. And the same also do apply to low MC. There are some variants of low MC which does not achieve the prescribed security level from NIST or G+. So to conclude, we did improve circuit implementations of spec and low MC. The techniques that we applied are borrowed from both quantum and classical domains. They can be utilized to have better implementations in classical setting. But what we definitely showed that the security bounds are significantly less than what is imagined by having our implementation. And this is not all. We know that there are more optimizations possible in this ciphers as well as other private key ciphers. So this is a very exciting and new domain. There are lots of work to be done. So I invite you to participate in this kind of research. And with this, I would like to conclude my talk. If you have any questions now or later, please feel free to reach out. Code is publicly available.
Another quick question. So there is a trade-off between the number of qubits and the data, right? So the common person study or you have performed that how much you can increase to go how down like the limit. So that you can claim, okay, my circuit is the optimal one, you cannot go there.
So there are some optimizations also in the classical setting. We know that which can reduce both depth and the number of qubits. So we are trying to, we are trying to push the Pareto curve below. And only after we know this is the best possible, no further optimizations done, then we start talking about trade-off. So initially started thinking of we will reduce the depth, but then we ended up getting a lot of points where we see both are being reduced. And this is not even covering the whole spectrum. Yeah, like you can do more parallelization in the low MC rounds, key schedule, new adder instantiations, different adder structures. Yes.
There are no more questions. It's time to see them.
Hi, can I have a question?
There is a question from online.
Hello.
Yeah.
May I have a question?
Yeah,
Yeah, thank you for the talk. And I was just wondering, have you compared the DW cost with the previous implementation?
Mhm.
I mean the depth times the width of the circuit.
Mhm.
Yeah. So in considering the DW cost, does the implementation of yours is better than the Because in your comparison, you compare either the
Can I
case
take the
number
question offline, because I
or
think I need to
the
really look
depth
into the code
difference.
and the algorithm for the details that you're asking for.
Sorry.
Hello, yeah. So I request to the online participants, because we already ran over time. So I request you to ask this question offline. Maybe you can email the author.
Okay, thank you.
Yeah. Okay, so the next talk of this session is on the security notions for encryption in a quantum world. I think it will be presented online by Chevalier, Abrahami, and Huifu. The connection is being set up, so please hold on for a couple of minutes.
Can you please share your slides? Yeah, you can share your screen. Hello, are you audible? Hello? Is the speaker present? Or you?
Can you hear me now?
Yeah, you can share your screen.
You disable the screen sharing, so I think you need to enable it first.
You can share.
Okay, I can share. Okay, thanks. You see my screen?
Yeah, thank you.
Just a second.
It's okay. You can. Your screen is not visible.
Oh, you do not see my screen?
No.
Okay, let me try again.
Huh? Now it is visible. You can start your presentation.
Okay, is this okay now?
Yeah, okay, thank you.
You see the screen moving? Okay. Okay, sorry for the delay. Hello, everyone. So I'm going to talk about a paper on security notion for encryption in a quantum world. So this is your work with Céline Chevalier and Ehsan Ebrahimi. So first, let me give you some motivation on our work by introducing like several different level of security model. So the most basic one would be classical security that we usually consider, in which we only have classical adversary with classical communication. And then we go up one higher level with a post-quantum security, in which the adversary now has some local quantum computation using some quantum computers. But then the communication still is classical. So usually for post-quantum security, you require a post-quantum assumption, for example, learning with error or syndrome decoding problem. And sometimes you also need to consider like a quantum random oracle model instead of just a classical random oracle model. And then if you go like even further, you can consider fully quantum security. So in which the adversary now not only have quantum computer, but he can also quantumly interact with like end user devices. So this live work has been started with Zanri in 2012 on constructing quantum secure zero random function, and few hours work on encryption and signature schemes. And the reason is that basically this security model guarantees the best security level that we can achieve because even in the worst case, like the adversary have control over the user devices. And you also reduce the assumption on the hardware. So like if imagine that like the end user run the classical algorithm on quantum computers, then we need some assumption on the hardware. Like you need to make sure that the measurement device implement correctly. And we want to reduce on the assumption that we on the hardware. And so our work in our paper, we focus on fully quantum security for classical encryption. So what do I mean by fully quantum security? Basically, we in the security definition, we allow the adversary to have a quantum access to the encryption oracle, which is modeled at like in the standard query model as this superposition of input X and some ancillary register Y, and the encryption X is will be XOR to the Y register, and only the thing will be returned to the adversary. And similarly, we can also consider the quantum access, like giving a quantum access to the decryption oracle in a chosen ciphertext security, in which the adversary now have the access to the decryption oracle. And so before our work, the first work on considering this notion is by Bonet-Zandri in 2013, in which they define a security definition for public key encryption and symmetric key encryption, in which the adversary can have quantum access to encryption and decryption oracles. But then the challenge phase is only classical. And then a new introduction was introduced in 2013, only for symmetric key encryption with chosen plaintext attack, chosen plaintext security, and but this definition allows quantum challenge phase, but restricted to a special minimum oracle. I'm not going into detail, but it's not some. In zero, the minimum oracle is some very limited oracles that cannot be implemented in zero. And so the open question would be to define a security notion for both public key encryption and symmetric key encryption with chosen ciphertext security in the standard query oracle query model with quantum challenge rate. And in the process of doing so, we have several obstacles, like from the quantum mechanics, basically. So we have the no-calling theorem, the destructiveness of measurement that prevent us from like copy and store the challenge ciphertext, and so it's not clear how to define the security. And there's also some impossibility when you naively translate the classical definition to the quantum setting. So in our work, we present a new security notion for chosen ciphertext security for both public key and secret key encryption, and we saw that it's achievable, basically. And the overview idea of our techniques is we first switch from a left or right indistinguishability notion, which is impossible to achieve in the quantum setting, as shown by Bonet-Zandri, to a real or random indistinguishability notion. And we also adapt the recent compressed oracle technique for random oracle to the encryption in the random one, so that we can record the challenge plaintext. And I'm going to describe the technique now. And to do that, first, let me recall the classical IND-CCA, so the indistinguishability against chosen ciphertext attacks in the real or random style. So the definition I present here is completely equivalent to the left or right on like the standard definition that we use, like currently used. And here is the example is given for symmetric key encryption, but you can adapt it to the public key setting. So the security is defined by experiment depending on the bit B between the challenger and the adversary A. So for the challenger samples uniformly a random secret key K, and then the adversary have two learning phases. In the first phase, the first learning phase, the adversary have classical access to the encryption and the decryption oracle, and he has to put a challenge plaintext X and some internal state. And then the challenger sample a random function from the domain of the message space. And depending on the bit B, the challenge plaintext Y star is encryption X, or the encryption of some random message by applying H to the X. So here's the definition as to the B. So if B is 0, we are in real one, in which the Y star is the encryption of X. And if B is 1, we are in the random one, in which Y star encryption of random message. And in the second learning phase, the adversary again has some has classical access to the encryption oracle and some modified decryption oracle, and he basically need to get the bit B of the experiment, and he gets bit B with like non-eligible bit. And the modified decryption algorithm basically return the original plaintext, challenge plaintext X if the query is the input is the challenge ciphertext. Otherwise, just use the normal decryption algorithm to answer the query. So that's the classical definition for chosen ciphertext security. And the idea now we want to give an analog for the quantum setting, in which the adversary have quantum access to the encryption and the decryption oracle, and he can also send a superversion of the challenge plaintext. So to do that, we use Zandri compressed oracle to try to record the query in the random one, because in the random one you have some random function involving in the security definition. And I will briefly recall the recording technique by Zandri. Basically, the goal of this technique to allow you to do on-the-fly simulation of random oracles in the quantum setting, and it has 4 steps. The first thing, we can do purification over the oracle raster. So instead of classically sampling uniformly at random of our function H, you can put the function H in like uniform superposition. So the oracle initial state can be considered as the full truth table of the function in uniform superposition. And instead and the second step, instead of doing the queries in the standard basis, we do it in the Fourier basis, basically by using quantum Fourier transform to the Y raster of the adversary and the oracle raster H, so the function raster. So the effect of this transformation that instead of XOR the output of the oracle to the adversary raster, we do the other way. We XOR the output of the adversary raster to the oracle raster. So here for the notation, P of X, Y is this point function that returns Y hat if the input is X and 0 on the other point. And the most important step is to do compress and decompress. So the main observation is like after Q query, the Oracle database basically has most Q non-zero points, and we can remove all the 0 points from the database. And but the way we do that is to consider basically the query of the adversary and the Oracle database D. So from the start, the Oracle database is empty, but then for each query, depending on the value Y, then you can either update the database or remove the record from the database. And the final step would be that we return back to the standard domain by again applying Fourier transform. And by doing so, like performing the 4 steps that I just mentioned, then the Oracle now also has information about the adversary queries. Basically, the Oracle's managed to record on the query that the adversary has made during the process, and it also give you the perfect similarity. Basically, like the compressed Oracle is a perfect simulation of the quantum random Oracle. And so the idea now we use the technique and we try to do the recording for the equation only in the random world. So we consider the equation in random world a function f of x and some randomness r as the equation of h of x with randomness r for some random function h. So the way we do it similar to the compressor technique. To the compressing technique. So the first step would also is to do purification. We put the function h in uniform superposition, and we look at the Fourier domain. But the main difference now, we do not apply Fourier transform on the h register as before, but we apply the Fourier transform on the f register, so the function register, and also on the y register of the adversary. So by the same computation, you exhaust the output the adversary register to the function register of the Oracle. And we do the compressing depending on the query x, y, and the database D of the Oracle. We can do the same thing as before. Either you update the database with a new record, or you remove from the database. And the last step again is we just reapply quantum Fourier transform to revert back to the standard domain. Okay, so we can show that the technique here allow you to record the query in the random one in the security definition, but there's some caveat. So the first, the most important point is that the above simulation needs like 3 applications of the encryption algorithm. So UF is basically the unitary that implements the encryption algorithm. And this is not really useful for several cases. For example, it is not really useful to when we want to prove a one-time security, when the primitive like the encryptions are only one-time secure, or you want to do some security reduction, for example. So our final observation is actually you can do simulation with just one cone to the encryption algorithm. The reason is that because in the encryption setting for each query, basically you sample a new randomness and new random function. So the database is on way initialized to 0. So basically in the step 3 that I mentioned before, you do not need to check to do on the decompress, compress, and decompress. So actually you can only simulate with just only one cone to the UF from the beginning. So that our final technique for recording the query in the random one in the encryption security definition. Okay, so here for some notation, then the Oracle database after the challenge phase is a list of randomness. So R would be classical value in superposition of X, U, and Y, where you use some random message, like some message in the message space. X is the challenge plain text, and Y is the challenge ciphertext. So using the technique, we can now define the QIND QCCA security notion. So it's the quantum indistinguishability against quantum chosen ciphertext attacks. The definitions as follows: you sample the transit sample secret key K, and the adversary have some quantum access to the encryption and the decryption oracle, so it's denoted using the cat notation. And he has to output some quantum state, which is the uniform superposition of some of challenge plaintext X, some ancillary rest Y, and some internal state phi. And then we the changer, depending on the bit B, is either encrypt the phi, the big phi state here, using the encryption algorithm, or applying some random function and do the encryption. So in the real one, so here we use the compressed oracle here, basically. So in the random one, you would have some database that are hidden from the adversary. So it's kept by the changer. So it denoted D, X, Y. Otherwise, in the real one, the database will be empty. So you basically have no database in the real one. And we return the quantum state, like the output here, the state here, to the adversary. And in the second learning phase, again, the adversary have access to the encryption and some modified decryption oracle, and the adversary need to make a guess on the bit B. And so the decryption oracle in the second phase, it use the database basically in the random one. Because for the real one, we always use the same decryption oracle. In the real one, we use the same decryption oracle for the first phase and this second phase, but in the random one, we use some modified decryption oracle that are augmented with the database D. So depending on the query, so Y will be some ciphertext and Z with some ancillary register. And if we find Y in the database D, we do not find Y in the database D, then we just use the decryption algorithm to answer the query in superposition. Otherwise, if we find some Y in the database D associated with the randomness X and U, then you return X as the challenge, the original challenge plaintext. So we XOR the X to the output register of the adversary. So that would be our definition for chosen ciphertext attacks, security. And again, you can do similarly for public key encryption. So there's some caveats on the definition. Basically, the main takeaway is that our technique only allow you to record the queries in the random one. So we must be really careful about how to use definition and the technique in the security proofs, because it's not like in the classical setting where you can just record both in the real one and the random one. And we know that in zero is we cannot record the encryption query in the real one if the encryption scheme is not secure in our notion. So in our paper, we also show some properties and achievability for our notions. For the properties, we saw that our notion is strictly stronger than the classical indistinguishability notion. And we saw that the notion is also composable, and we saw some several separation that you can find in the paper, and we saw that the bit encryption is also complete. It means that you have the bit encryption, and then you can do many bit encryption also. Yep.
Hello, please wrap up in 2-3 minutes.
Yeah, I'm finishing. Yeah, I'm finishing. And for the achievability result, we saw that in the symmetric setting, we saw encryption and PIF is QND QCCA, and for the public key setting, basically you can starting from any encryption scheme that is secure in the Bonnet-Zanry with classical challenge and one-way function, you can do we can achieve we can leave it to our notion. And that's all. Thank you for listening.
So any quick question from the audience or from the online participants? Okay, so if not, let's sign the speaker again. With that, session 9 is over. You must all be tired, but fascinating talk. Stop by Daniel Bunsen. Yes, the festival of this conference. We announced last night. Is Daniel?
I hope you can hear me. I'm currently finding my slides to share.
Yes, Dan. Yes, Dan. Yeah, I can see you.
Okay, can you also see my slides?
Yeah, yeah, I can see your slides too. Okay, Dan.
All right, great.
Before you start your talk, let me inform you one thing that this year we have this PCA sponsored the best paper ever, and your paper has been adjudged the best.
Oh, wow.
Okay, so
Well, thanks very much.
yeah, you would have been here, but anyway, so I'll get in touch with you about how to transfer the money.
Wow. Okay. So I'm honored. Thanks very much. Yeah. Also,
It's about $1,200.
I'm sorry. Say again.
It should be about $1,200.
Wow.
So we just transfer to your account. I'll get in touch with you. Okay, no. Dan needs no introduction. One of the most prolific researchers of today. Dan, please go ahead.
Well, thanks. Wow. Also, thanks for. I'm sorry for not being there in person, and thanks for making it possible to present and listen to talks remotely. Yeah, I have a paper online for this, and that one has a tag on it, which is listed on the first slide here, which is NTRU, but with a W instead of a U, so that makes it easy to find online. Of course, the U to W is flipping one bit in the ASCII character. I also want to emphasize an acknowledgement that you can find in the paper, which is that this draws heavily on a series of discussions that I had with Tanya Lange about chosen ciphertext attacks and defenses. And this includes in particular major motivation here, which is that she was pointing to plaintext confirmation as a countermeasure to fault attacks. Okay, let me jump into the context, which I want to emphasize post-quantum deployment. So starting with, in April, OpenSSH version 9 turned on post-quantum crypto by default, specifically, well, a combination of two crypto systems. One of them is an old elliptic curve crypto system, which is just to make sure that if something goes wrong with the new crypto system, then we're not losing security. So encrypt with that and encrypt with a new post-quantum crypto system, Streamline NTRU Prime. And then in July, NIST finally said, all right, we've selected an encryption system, post-quantum encryption system, namely Kyber, along with some signatures, which I won't talk about. And then in November, Google said all of their internal Google networking, which is a lot of important network data, which we know attackers have been trying to record for many years and trying to decrypt. Well, they said that they are encrypting all of that, again, with a combined system, a hybrid, a double encryption with an old elliptic curve system, which will be broken by quantum computers eventually, but at least we're not losing security for the moment, plus NTRU HRSS, which is the crypto system I'm talking about today. Now, you might say, wait a minute, if NIST said they're standardizing Kyber, then why is Google saying they're rolling out NTRU HRSS? And well, Google had an answer for that, which is, well, Kyber, it's fast, but patents. So what's going on with patents? Well, you can find various details in, I'll point to the NTRU Prime frequently asked questions list, which points to several specific patent families. And then if you get into more of the details, then, well, there's lots of complicated details inside these patents. Plus, really important thing to keep in mind when you read a patent, most important mistake that people make if they're looking at a patent is thinking that the patent means exactly what it says. That's not how courts interpret patents. What courts say is you're infringing a patent if you're doing, obviously, if you're doing exactly what the patent says, but also if you're doing something equivalent. And so courts ask, are you doing, well, basically the same thing in basically the same way? And then it's up to courts to figure out what the equivalence is there. So don't make the mistake of treating patents as something literal. It's up to courts to figure out if you're doing something that's close enough to be covered. And so you really have to look at how courts analyze these things to understand what the scope is of patents. Well, NIST made some serious progress that they announced also in November last month, where they've announced licenses for 2 of these patents. Maybe the others don't apply. You need to analyze this. The analysis is missing for the moment. More important issue with these licenses is that you might have heard about Kyber 1024. Well, on the slides, there's a reference to Kyber v 2024. That's not Kyber 1024. What Kyber v 2024 means is the version of Kyber that is going to be standardized in 2024. And at the moment, we don't even know what that is. There's discussions of modifications to Kyber, which will go into the standard maybe, and well, depending on current discussions and what NIST decides to do. And once that's defined and standardized, then you're free to use it under these licenses. That's what the license text appears to say. But well, right now we have a problem, which is that attackers are recording traffic right now. And once they have a quantum computer, the attackers will be able to understand it. And so every day that we're not deploying something is we're failing to provide security for these users who need their data to be secure for a long time. In some cases, maybe your data doesn't need to be secure for a long time. You're watching some, fun video online, but there's lots of data that really needs to be protected. And well, we have to roll something out. We're already many years late in doing this. So, okay, enter HRSS for people who are rolling something out right now, like Google. It totally makes sense for them to pick something unpatented, like Enter HRSS. And Enter HRSS, it's also small and it's fast. Maybe sometimes it's not as fast as Kyber, but it's fast enough. You can use it. And so, great. Enter HRSS, perfectly reasonable solution, but is it secure? So that's what I'll talk about for the rest of the talk. And this is something where, of course, the original HRSS paper says, well, Entru has a track record of surviving 20 years of cryptanalysis, and they look at security in more detail than that. I mean, the HRSS paper looks at more, and I'll say something about what they're saying. But already that sounds good as a starting point. 20 years of Entru before 2017, Entru survived cryptanalysis. If you look more closely, you see that the lattice attacks have been doing a lot of damage and breaking a lot of key sizes. You need bigger and bigger and bigger keys to resist lattice attacks. But okay, you can still, if you have big enough keys, then seems that you're okay. And hopefully at some point the lattice attacks stop getting better, and then good, we've got key sizes that are big enough. All right, so the system as a whole seems to be surviving, even if a whole lot of specific key sizes that were proposed did not survive. All right, the HRSS paper proposes various improvements to Entru. So they say, well, here's some things you can do to make it more efficient, for example, and then they say for security, you can upgrade the security provided by the original Entru system. The original Entru system is only designed to be passively secure. And the HRSS paper says, well, we can turn this into something which resists chosen ciphertext attacks. Specifically, they say we can turn this one-way secure encryption system into an IND-CCA2 secure key encapsulation mechanism, CAM. Great. Now, how do they do that? Well, they apply what's called the Fujisaki-Okamoto transform, FO. And this is a whole class of transforms, actually. Already F&O had a bunch of variants of this, and then many more variants in the subsequent literature. And well, let me look in more detail at what this does. First of all, there's 2 major points I'll emphasize. First of all, defense 1 is re-encryption. So what this means is that when you're decrypting, you get a ciphertext for whatever public key encryption system, you decrypt it. And then to make sure that the ciphertext is kind of rigid and matches this plain text M that you got out of decryption, you re-encrypt M and you compare it to the ciphertext, and you reject the ciphertext if that doesn't match. So the idea here as a chosen ciphertext attack defense is that, well, if the attacker is trying to modify the ciphertext and see which variants of the ciphertext produce the same plain text, which is how many chosen ciphertext attacks work. It's not everything, that's why there's more defenses, but a lot of attacks work this way of tweaking the ciphertext and then saying, some of those variants of C decrypt to the same M. Then that's something which you block by saying we're going to re-encrypt and make sure we get the same C. That means that there's only one ciphertext that can give this M. So all of the variants will fail and the attacker doesn't learn anything from that. Now, this re-encryption, you should be thinking, if, wait a minute, there's a randomized encryption system. I mean, your public key encryption systems are supposed to be randomized, right? Because if you have a message which an attacker might guess, then you need to have some extra secret randomness coming in so that the attacker can't verify, do their own encryption of the message passively and see, does that match the same ciphertext? So textbooks will say, of course, you have to randomize your public key encryption systems, which means that your re-encryption will also not give the same ciphertext. So re-encryption sounds like it doesn't even work as a crypto system, never mind security. But you can first, before applying re-encryption, important part of the FO transform is to de-randomize your encryption. So what that means is you take your message M and then you hash it with, pick some reasonable hash function, and that gives you a string of random bits, and you use those random bits, which is a deterministic function of M, you use those random bits as the randomness inside your encryption process. So whatever randomness was used for encryption, you de-randomize, you choose the random bits as a hash event. This is dangerous because, again, the attacker might be able to guess what M is. So you must only apply de-randomization if M has high enough entropy. For example, 256 bits of entropy, that's enough. The attacker won't guess 256 bits. But if M has less entropy and the attacker can guess that, then because there's no other randomness coming in, the attacker can just try computing the encryption function of M and see if that matches. So you don't want to have a low entropy M when you're de-randomizing to apply the FO transform. I'm emphasizing this because people often do this wrong. For example, Frotochem. Frotochem claimed, actually, they still haven't withdrawn this. Frotochem claimed and claims that their parameter sets comfortably match their target security levels with a large margin. And that's not true because M does not have high enough entropy for that. And actually, if you try to increase the entropy of M inside Frotochem, then everything, the keys plus ciphertext, gets quite a bit bigger. So you really have to be careful about the randomness coming in. Anyway, entry HRSS has enough randomness in M. Everything's fine for the re-encryption process. It just works. Great. So the attacker cannot have a different ciphertext producing the same message. And also the attacker can't just guess messages because there's too many possibilities. Now, there's another defense, defense 3. Why is this 3? Well, that's because in my paper, I have a certain categorization of like 9 different features of crypto systems which interact with chosen ciphertext attacks. And well, this ended up being defense 3. For the talk, you don't need to worry about what defense 2 is. I'm not going to say anything about it, or defense 4 and so on. Well, actually, I will get to 4, but okay, anyway, this is defense 3, which is plaintext confirmation. So plaintext confirmation says that you have your public key encryption function E, and you have a ciphertext E of M. Well, plaintext confirmation extends that ciphertext to include another hash of M. So this, you don't need any mathematical structure for this function H prime here. This hash function is just some normal hash function, and you include that hash in your ciphertext. Now, when you're decrypting, well, you don't need this extra hash. You can just ignore it and decrypt using the mathematical public key encryption function E, like you normally do. You take E of M and decrypt that to get back to M. But when you're re-encrypting, which is part of the decryption process now from defense 1, you make sure to check the hash. So how does this stop chosen ciphertext attacks? Well, a lot of chosen ciphertext attacks are using the mathematical structure of E to have modifications of M, which give modifications of E. For example, in RSA, you have a multiplicative structure. And when you have a message and you, for example, cube the message, then RSA is just taking a power. So you cube the ciphertext in RSA. And then that's the sort of thing that is used in various chosen ciphertext attacks. Now, in lattice-based cryptography, like entry HRSS, you have a linear structure. And E of M plus 1, for example, can be closely related to E of M. You have to look at how big M is and how big M plus 1 is. And well, this is something the attacker can learn information from using the linear structure of E. by modifying E of M to get E of M plus 1 and various other M plus other things, the attacker can figure out a lot of information about M depending on which of those are going to decrypt correctly. When you insert a hash function, this plaintext confirmation, into the ciphertext, then, well, you stop the attacker from producing a valid ciphertext for M plus 1, because how is the attacker going to figure out H prime of M plus 1? Well, sometimes people propose hash functions which are sort of linear, but let's just take a normal, unstructured, proper, symmetric crypto kind of hash function. Then there's no way to take a hash of M and turn it into a hash of M plus 1, unless the hash function is really, really weak. So, okay, great. So this stops this class of chosen ciphertext attacks. And these are the major defenses that come into the FO transform and are applied inside HRSS, and great. Nobody knows how to attack this, except current enter HRSS is different. Current enter HRSS says we're going to adopt a variation of the original enter HRSS, which was proposed by Saitong, Sagawa, and Yamakawa, and has some interesting features and definitely has some advantages. But there's one part of it which is kind of scary, which is that it removes plaintext confirmation. Now, I was just saying how plaintext confirmation blocks a bunch of chosen ciphertext attacks, and well, it's not that they ignored this. They said there's another defense. So this is defense 4, which is implicit rejection. Now, what does implicit rejection mean? It means when you have a key encapsulation mechanism, so you decrypt your message and then hash that with another hash function to produce a session key, like a 256-bit AES session key. Instead of throwing away invalid ciphertext and returning false, something that blocks the decryption process from producing a result, what you do instead is you produce a pseudo-random result. So you take the ciphertext, which was going to be rejected, and you say, no, we're not going to reject it. What we'll do is we'll hash it together with a random string R. So this is, say, 256 bits stored inside your secret key, separate from everything else. You have your secret key plus a 256-bit string R. And you hash this random string R together with the ciphertext. Or you can apply other PRFs, and that's fine. The point is you have a 256-bit secret key R as part of your decryption secret key. And then you use that to, well, encrypt the ciphertext, produce a pseudo-random result. Now, how does this stop chosen ciphertext attacks? Well, there's an answer to this, but it's a question, it's an important question that you have to worry about, because if you're throwing away plaintext confirmation, which clearly is intended to and apparently does block a lot of chosen ciphertext attacks, if you're throwing that away and saying, let's use implicit rejection instead, then you have to worry, is implicit rejection accomplishing what plaintext confirmation does? It's not structurally clear that it does this. Well, the answer to this in the SXY paper from 2017 and in the updated Enter HRSS proposal is there's a proof. If you have OWCPA, so you assume the underlying entry system that survived 20 years, assume that's achieving what it's supposed to, and you put in implicit rejection and re-encryption, then here's a proof of in CCA2 security. But if you look more closely, then you start worrying about whether this is really answering the question. First of all, what's proven is only QROM in CCA2 security. So there's this model of chosen ciphertext security in CCA2. And then within that, there's a narrower class of attacks. And we know some attacks which are outside this. There's a narrower, not against Enter HRSS, but you can write down easily crypto systems that have non-QROM attacks against NCCA2. And well, okay, the proof is only looking at QROM, this narrower model, QROM in CCA2. So are there attacks outside this model against HRSS? The proof does not say anything about that. Second question is, well, the proof is actually loose. You have to go down to an even narrower model, which is ROM in CCA2, to have the proof being tight. Now, tightness means that your security, your NCCA2 security matches your OWCPA security. But in QROM in CCA2, what's proven is you don't lose more than a certain number of bits of security, but that's a pretty big number, which means that HRSS could be broken in QROM in CCA2, even if the OWCPA security is high enough. Maybe. The proof just doesn't answer this question. And then issue 3, I'm not going to talk more about issues 1 and 2, but issue 3, which I will talk about, is this INCCA2 model covering all chosen ciphertext attacks? There's a real world concept of chosen ciphertext attacks. There's a mathematical definition in CCA2. Do these things match? So there's actually 4 different models here. There's ROM in CCA2, there's QROM in CCA2, there's in CCA2, and then finally there's actual chosen ciphertext attacks. And the mismatches here might mean that the proof, which is completely satisfactory in the middle, the proof might not be covering all the chosen ciphertext attacks we care about. And there might be a serious problem as you go farther and farther out in these 4 different concepts of what's going on. Okay. I'm reminded when I look at this situation of a quote from Neil Koblitz from 2007, where he says, anyone working in cryptography should think very carefully about dropping a validation step that had been put in to prevent security problems. There I'm thinking, okay, plaintext confirmation. Certainly someone with Kravchuk's experience and expertise would never have made such a blunder. He's talking about a broken crypto system, HMQV, if he hadn't been overconfident because of his proof of security. Okay, this is another case where there's a proof, and the proof, if you narrow down enough, then the proof is correct and does what we want it to do. But the problem is, does the proof for implicit rejection, does it cover all the chosen ciphertext attacks that we care about? A lot of times people say, oh, the particular issues of proofs being a problem, that's a rare thing and doesn't happen very often, so you don't need to worry much about it. But there's an amazing paper from Koblitz and Menezes in 2019 where they're cataloging more than 100 different proof failures and explaining how these different failures work and pointing to references for everything. And so you really can't ignore the possibility that there's a proof failure going on here by narrowing the narrowing down from chosen ciphertext attacks to ROM in CCA2. All right, so we should think very carefully before dropping plaintext confirmation. And well, this is something which already started in 2018, and I would say even earlier, people looking at this question of whether implicit rejection is good enough as a replacement for plaintext confirmation. I wrote a paper together, this 2018 thing was with Eduardo Persichetti, where the main point was looking super closely at that ROM in CCA2 proof and factoring that into small separately verifiable pieces. And yes, that proof is correct. There's not a failure in the small model of the proof being invalid. The proof is valid, that part is correct, tight, etc. But we also looked at the question of, well, can you equate that small thing with the big thing? Is it safe to be saying that implicit rejection is good enough? And we said that, well, implicit rejection and plaintext confirmation, the idea from an attacker's perspective of why implicit rejection is a problem is that when you have a variation of your ciphertext, an encryption of M+1, then, well, if that gets rejected and then implicit rejection kicks in, then what implicit rejection does is stops you from seeing that there was a failure. So late in the attack, when there's an output telling you, yes, you've successfully encrypted M+1, starting from an encryption of M, or no, you haven't, implicit rejection changes the haven't case, the rejection, to pseudo-random data, which you can't tell the difference between that and something that was a valid encryption of M+1, because you don't know what M+1 would have produced. It's just 2 random things. I mean, it does feel like it's stopping an attack if you think about it, but it's at a different stage of the attack from plaintext confirmation, where before anything happens with this message, you're just immediately running into this obstacle of you don't know H prime of M+1. All right, when we said current proofs, plaintext confirmation and implicit rejection are accomplishing the same thing for the proofs, but because there's different stages of the attack being handled by these defenses, and because we don't have proofs which cover everything that we might care about, it's difficult to justify recommending against the dual defense of doing both plaintext confirmation and implicit rejection. But that still doesn't answer the question of whether there really is a problem. I mean, maybe this could be fixed by more of a proof or more analysis. On the other hand, maybe there's an attack. So that brings me to one slide about what this paper is doing, and then I'll have one slide on follow-up work and stuff. So what this paper is doing is, first of all, as a reminder, hardware is not perfect. And in particular, DRAM, so dynamic random access memory, where gigabytes of data are stored on your computer, that hardware has failures naturally. Google collected statistics, which if you say, what does that mean for, say, 10 to the 9th users who each have a 256-bit key in DRAM, Google statistics measurements on their servers say that you're going to have somewhere around 100,000 keys that are corrupted every year. What the corruption is the DRAM. I mean, you have a bit 0 sitting there, 0, 0, 0, 0, 0, and you expect that it stays at 0 unless you actively change it. But the DRAM, because it fails, the 0 will occasionally just change to a 1, and then it's going to be 1, 1, 1, 1, 1. So the bit is corrupted without your doing anything. This is a fault that naturally happens to a significant amount of data. Most users are fine. But in cryptography, we worry about attacks with probability 2 to the minus 50. Of course, we should worry about an attack with probability 10 to the minus 4. Okay, in the paper, what I'm doing is saying the main thing is simply this one line that if you have a bit flipping inside this R that comes into implicit rejection, then that completely breaks the security that implicit rejection is supposed to provide. Because think about an attacker who sent a ciphertext with the old R and then sends it with the new R, same ciphertext. Then, well, implicit rejection is going to give a hash of R comma that ciphertext with the old R, and then later hash of the ciphertext comma the new R, which is different, unless you found a hash function collision, which would also be cool. And then, okay, so you've got these two different values, which is exactly telling the attacker, aha, you've had a rejected message, which is what the attacker was trying to figure out that implicit rejection was supposed to stop. Okay, so the attacker sees which ciphertexts are invalid, and well, then applying this to enter HRSS is working through a standard type of lattice chosen ciphertext attack, which hasn't been done for enter HRSS, and that's a bunch of details, but it's, I would say that part is kind of standard. The main thing to remember is that implicit rejection is something which is really fragile if any data gets flipped. All right, so finally, oh, I'm sorry, I have a little more about countermeasures. I worry that I'm out of time, so let me just peek at my watch. I think I am out of time, so I'm just going to flip past this and do the final slide here, which is about Classic McLeese. So Classic McLeese said, after this paper, they said, okay, we're going to drop plaintext confirmation, at which point you should say, yikes, why are you doing that given this type of attack? And Classic McLeese says, well, this is because there's a patent, which doesn't seem like it applies to Classic McLeese, but well, because courts are, a little unpredictable, let's just make sure absolutely that we're safe. So let's get rid of plaintext confirmation, because plaintext confirmation is a major part of that patent. And then getting rid of it is clearly separating from the patent. The Classic McLeese documentation says along with this, well, this means that there's a problem whenever you have a bit flipping inside R, and then says, well, apply error correcting codes to stop this. So this is not elliptic curve cryptography, this is error correcting codes. And then that's something you have to worry, where is that in your crypto system, these error correcting codes? And well, Classic McLeese says it's better to not put error correction into each individual chem. Instead of having every specification say, here's how you do error correction for this, it's a general purpose transformation. Specify that separately from the crypto system. That makes the design of each chem easier to design, and each chem is easier to review. That's it. Thank you for your attention.
Question? Not running out of time. Question? Otherwise, let's try the time on board. First stop of the conference will be video, but will be online. So it will be is prepared by Shiji Yang Song, Jung Chu, Shwedi, and Ding Feng Ye. Shiji Yang Song is making the presentation. You don't like? Yeah, postpone. Because whatever we see
Right.
6 point.
Yeah, is it all right? Yeah, I can see that. Yeah, so. Okay, so we're running the video.
Hello everyone, I'm going to present the paper. An efficient key recovery attack against N2 re-encrypt from Asia CCS 2015. I'm Zijian Song from State Key Laboratory of Information Security, Chinese Academy of Science. And this is a joint work with Professor Jun Xu, Dr. Zhiwei Li, and Professor Difeng Ye. Our contribution is mainly on 2 points. First, we propose a key recovery attack against N2 re-encrypt. N2 re-encrypt is a proxy re-encryption scheme based on N2. For specific parameter sets like these, N2 ring Z sub Q mod X to the N minus 1, and the N in the red box corresponds to the red parameter above. The number of ciphertexts required to complete an attack is on the order of 10 to the 3. And the running time is 1 hour on PC. Then we focus on other instances of N2 re-encrypt. As for N2 parameter sets in the third round of NIST PQC completion, the number of ciphertexts required is O(n) squared. The content of our report is divided into 4 main sections. Preliminaries, key recovery attack against N2 re-encrypt. Other instances of N2 re-encrypt, and the conclusion. First, we introduce the basic notations. The basic ring is quotient ring R equals Z sub Q X mod X to the N minus 1. PQ are integers, where P is much smaller than Q, and the GCD of PQ equals to 1. Ternary polynomials T D1, D2 means a polynomial with D1 entries equals to positive 1, and the D2 entries equals to negative 1. Polynomials used in N2 are divided into 3 parts. Private keys LF equals to ternary polynomials TDF and DF minus 1. LG equals to TDG and DG. Secret polynomials LR equals to TDR and DR. Messages and polynomials with every coefficient of M lies between negative P minus 1 over 2 and positive P minus 1 over 2. Now we introduce N2 scheme. In this paper, N2 parameter sets are as the same as the work of PQC Crypto 2019. The specific set of parameters is shown in the table. DG, DF, and DR means the parameter in the ternary polynomials. In such N2 schemes, the private key F has changed a little. First, choose capital F from ternary polynomial TDF, DF. Then calculate F equals to 1 plus P times capital F. And there's no change in the rest. Then a brief introduction to N2 encryption and decryption. In key generation, randomly chooses capital F from TDF, DF, G from TDG, DG, and calculate 1 plus P times capital F to obtain F. Then can obtain private key pair SK equals FG, public key PK equals H, and H is calculated by the following equation. Alice encrypts one message M from LM. She should select a secret polynomial R from LR and calculate H times R plus M mod Q as the value of ciphertext C. Bob decrypts C by his private key F times C mod Q to obtain A, and make sure the coefficients of A are all lying between negative Q over 2 and positive Q over 2. At last, calculate A times the inverse of F mod P to obtain the message M. Now we introduce N2 re-encrypt scheme. N2 re-encrypt needs to generate a proxy re-encryption key RK. First, use key generation algorithm to produce Alice and Bob's key pairs PKA, SKA, and PKB, SKB. Alice chooses a polynomial T from RQ, then sends T to the proxy and calculates T times FA mod Q sent to Bob. Bob uses T times FA, then times the inverse his private key FB, and also sends to the proxy. Now proxy can calculate the re-encryption key RK equals FA times the inverse of FB mod Q. The operation of N2 re-encrypt is shown in the figure. Step 1 in the red block is as the same as N2. Alice encrypts message M as ciphertext CA and sends to the proxy. Step 2 in the red block uses the re-encryption key RK. First, randomly chooses secret polynomial E for LR, then calculate CA times RK plus P times E mod Q as re-encrypt ciphertext CB. Bob can use his private key FB to obtain the message like N2. By the way, the point of our attack is here. Now we come to the details of our attack. Here are our main results. Our attack assumes that Bob or Alice is a malicious receiver or sender. In a situation that parameter dr of secret polynomial TDR is certain, and then an attacker can recover another's private key directly. Here is a compression of work with PQ Crypto 2019. PQC needs huge amounts of ciphertexts, nearly 10 to the 17, and chosen plain texts. Our work needs small number of ciphertexts, just thousands, and our attack has no registration on the ciphertexts. Our experimental results for specific parameter sets are below. As for different parameter sets, the number of communications of our attack are always only a few seconds. The running time are always in 1 hour on an Apple M1 CPU laptop. Our attack is divided into 3 steps. Step 1, construction of equations. we focus on the re-encryption stage. In this equation, we can find that the secret polynomial E has the special structure. Its coefficients exist in only 3 cases: +1, -1, and 0. And the number of +1 equals -1 equals dr. To take advantage of this, we write the above equation in the linear form. Bolded lower cases ECB means the vector form of ECB. Bolded uppercase CA means the matrix form of CA. That is the circulant matrix of CA. Lambda means the vector form of re-encryption key RK. That is what we want. Assume that Bob is an attacker. He can receive CB by legal communication and catch CA for public channel. Now the unknown variable is lambda and E. Then we do the inner product on both sides of the equation. We can find that the left side is a fixed number. Now the right side has only the lambda unknown. So we have successfully removed a variable E. Step 2, minorization. For convenience, we take the following notation to simplify the equation. In the bottom equation, all variables are known except lambda, but we still find a problem that the number of variables lambda is too much. Let Q equals 2 to the gamma, and uses the relationship between below to obtain a new equation. In this way, the variables lambda in the equation is partially replaced with x. Further, assume that C0 and U are even. We can divide both sides by 2 to obtain a new equation. Up to this point, we can count the number of variables. Is n plus n over 2 plus 1. It means that if we collect enough equations, that we can obtain the value of lambda mod q by solving the system of linear equations. Considering Bob is an attacker, he has private key FB, and he can use the equation in red box to get Alice's private key FA directly. Step 3, recovering private keys. As mentioned before, we were able to obtain RK mod Q by solving the equations. But the number of variables in the equations is too large. Solve the equations on Z2 to the gamma minus 1 or ZQ is costly. So we turn to solve the equations on F2 to obtain RQ mod 2. Actually, we just take few seconds in the experiment on F2. Now we try to find another way to get a private key. First, get position of the 0 bits of FA. The re-encryption key generation equation holds in ZQ and necessarily in F2. Then move to the term to get the equation in the red box. Besides considering key generation of FA, capital F is ternary polynomial with df +1 and -1. So we can turn to the equation to the blue box. We can calculate the right side. Since 0 bits mod 2 is not affected, then we can get position of zero bits of capital F. Further, the position of the zero bits of Fn. Secondly, get position of zero bits of Ga. Back to public key generation, it also holds on F2 in red box. Ga is ternary polynomial with dg positive 1 and negative 1. Then we can obtain equation in blue box. Like first step, we can calculate the right side. Here we have already got the value of Fa in first step. Then we can get position of zero bits of Ga. At last, we build and solve new equations. We plug Fa into the equation of public key generation and got a new equation. Here, P, Ha, and part of F and Ga are known. This is because we have got the position of zero bits of F and Ga before. Now we write as linear form. In red box 1, n minus 2 times df bits are known. In red box 2, n minus 2 times dg bits are unknown. So in the equation above, there are only 2 times df plus 2 times dg variables unknown. According to parameter set we use, this value is less than the number of equation n. That is, we can solve the equations and obtain the rest bits of capital F and Ga. Then we completed the key recovery attack. It should be pointed out that all the running time needs to solve the equation is only a few seconds. That is, due to our improvement, the time required to solve the equations is all negligible. Now we introduce other instances of N2 re-encrypt. In this case, we discuss N2 parameter sets in the third round of NIST PQC competition. Here are our results. We also assume Bob or Alice is a malicious receiver or sender. In the case that parameter dr of secret polynomial TDR is uncertain, no more a fixed number, then an attacker can recover another private key directly. The number of ciphertexts grows to O(n) squared. The following table shows our conversion results. The fourth row is the result of our first attack, and the second row is the result with the N2 HBS scheme as an example. Now we briefly mention our analysis ideas. We can find that, unlike our first attack, there is no information on the number of coefficients in the secret polynomial E. Due to the coefficients of E are positive 1, negative 1, and 0, we can use another property, ER equals to the cube of ER. Separate P from re-encryption equation and write as linear form. Use this property to explain the right side of the equation. We can find that only R is unknown. The number of new variables is the cube of n. Since one communication produces n equations, so the number of communications is O(n) squared. Here is our conclusion. Our attack is based on a special structure of secret polynomials from the set LR. For the question is how to reduce the number of variables in the equation and apply the attack method to another cryptographic schemes. That concludes my report. Thank you.
Line. Otherwise, let's thank the speaker once again. Dan and Tom. That brings Indocrypt to 2022 end. Thank you all. So I'll just probably finish off this conference with announcement and a lot of thanks to everybody who was involved in this event. First, let me start with the thanks. I think the first thanks goes to the program co-chairs. Anybody is away is there and Shantanu Shaka. Next is and this team Nilanjan, Chatterjee, Rakesh, Laltu, the entire TCG group, bodies and also the group of Vidul and others at ISAC. So we have done thanks to the Post Institute who have provided this wonderful facility free of cost. So thanks to this institute. There are a lot of people involved with this work and everybody is there. So I thank everybody, including the supporting staff of this institute. And finally, the thanks to our cameraman for taking this, recording the talks and so on. Lastly, all the participants, which makes this conference a success every year. The announcement is that we have a group photo outside after tea or before tea. So just let's assemble. Downstairs or on this floor?
The stage, in the stage, sir? Yeah, now.
Good picture here, sir. First thing that announced is that Indocrypt 2023 will be held in Goa, hosted by Bits Pilani Goa campus. The program is for Mr. with us, Anupam Chattopadhyay, Stephen Pisek. Sir. General co-chairs are our Indival Gupta and Suman Kundu with the director of Bits Pilani Goa. Let's look at the group photo and then have to.
Once announcement that participants who are registered with the Google form, registered in the Google form,